Hello.
Deepak.
Hi, Sue.
Hello, am I audible?
Yes, yes.
Okay. So previous session we discussed logistic regression. So logistic regression is a probabilistic classifier because here we are predicting probability, right? So we can use logistic regression for binary classification problem, right? So it's a binary classifier, and using this classifier, we can get probabilities, right? So if we are having two classes, for each class, we will have probabilities, right? And to getting probability, we will use this equation, right? So theta transpose x is the same as the linear regression model, right? Because in linear regression model also we are calculating theta transpose x, where x is the input and theta is the unknown parameter that we are learning here, right? So once we know the optimal value of theta parameters, we will use theta transpose x, and then we will apply sigmoid function or logistic function. So since we are applying here logistic function, so that's why this method is called logistic regression, right? So in this in logistic regression, we are having regression term, but it's not a regression problem. It's a classification problem, right? Binary classification problem. Yes. So we will calculate here probability. Probability p hat is equal to sigma theta transpose x, right? Now, this is the property of sigma function that it will convert values in between 0 and 1, right? So you can put here any t value, uh, positive value, any negative value, and it will convert values in range 0 to 1, right? So for positive t values, the sigmoid function will convert values 0.5 to 1, and for negative values, it will convert values 0 to 0.5, right? So for all positive values, we will get here output. In output, we will get 0.5 to 1, right? And for all negative values of t, we will get output values from 0 to 0.5, right? So here we are getting values from 0 to 1. So that's why we can say that here in output we are getting probabilities, right? Because in probability also we will get values from 0 to 1, right? So now here, if values output value or probability value is greater than 0.5, which means positive class, because for t is greater than 0, we will get probability score greater than 0.5, and for negative class, we will get probability score less than 0.5, right? Yes. So if output probability is greater than equal to 0.5, which means positive class, else negative class, right? Yes. And the same equation we will use at the test time, right? Once we know the optimal value of theta, we will use this equation to get the prediction, right? So if let's say for any given test input x, we will calculate theta transpose x, and then we will apply sigmoid function. And let's say after applying sigmoid function, if we are getting probability more than greater than 0.5, which means positive class, else negative class, right? So same equation we will use you will use at the test time also, right? Yes.
Um,
Then we, yes.
yeah, one quick question. You said that this is ideally a classification problem, but called regression. Is it only because that the values which we get is from 0 to 1 or a number, or there's some other reason why it comes under regression?
No, 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 no. Actually, here, see this. What is the theta transpose x? The same equation we are using for regression problem, right?
Yes.
So, so theta transpose x, the same equation we are doing for linear regression, right? But since here we are applying this sigmoid function, logistic function, and this sigmoid function is also called logistic function, right? Yes, this function sigma t is equal to 1 divided by 1 plus e minus t. This function is called sigmoid function or logistic function. So that's why this method is called logistic for the sigma region, and regression for this theta transpose x. But what finally we are doing? We are finally calculating probability, and we are applying here some threshold, right? So here threshold is this cutoff value 0.5, right? Eh, Because if you see this the graph of sigmoid function, here cutoff value is 0.5, which means for t is greater than equal to 0, this the output value will be greater than 0.5. For t is less than 0, output value will be less than 0.5. So since here we have applied this thresholding, and after applying this thresholding, in output we can get only two values, right? Either probability can be greater than 0.5 or less than 0.5. If greater than 0.5, then positive class, less than 0.5, then negative class. So what finally we are doing? We are finally doing a classification problem, binary classification problem. So that's why logistic regression is used for binary classification. The only difference is this is a probabilistic classifier, because in output we are deciding on the basis of probability, right?
Okay. Is it um, I mean, over here, the threshold is 0.5. Is it
Mhm.
always 0.5, or we can actually decide what the threshold should be?
No, so let's say for this in this case it should be 0.5, right? Because probability always range from 0 to 1, right?
Yeah,
So
no, no,
ideally, yes.
no, no, go ahead.
So so in this case, we will always take this 0.5, but yes, we can also change it depending upon our requirement. So let's say if we want to be biased for the positive class, right? So what we will do, we will shift this threshold, right? So let's say if we want to tweak, let's say if you want to increase precision or recall, then in that case you can also vary that threshold, right? Because let's say if you change this threshold, let's say from 0.5 to 0.6, then what will happen, right? Some positive example will be considered as negative, right? Or let's say if you decrease the threshold, then some negative examples may be considered as the positive example. So if you want to give more weightage to positive, or let's say more weightage to negative class, then we can also change it. But let's say if we are giving equal weightage to both positive and negative, then in that case we will generally fix it this value to 0.5, right?
Okay, got it.
Yes. So training and testing also we have discussed. So here we will use these two log functions, because here what we want? We want if let's say the actual output is 1 and model is also predicting 1, then we want zero loss, right? If actual output is 1 and model is also predicting 1, then we want zero loss. If actual output is 1 or the actual output is positive class, but model is predicting negative class, then we want here some loss, right? So as you can see here, if the actual output is the positive class, but model is predicting negative class. In that case, there will be infinite loss, right? If you use this equation minus log p hat, then this satisfy our condition, right? Because what exactly we want? We want high probabilities for positive instances and low probability for negative class. If input belongs to the positive class, then we want high probability. High probability means probabilities, uh, let's say 0.9 probability, 99 probability, that type of probability we want, right? Similarly, if the input belongs to the negative class, then we want low probability. Low means let's say point 0.1 probability or 0.001 probability. So that type of probability we want, right? Because as you can see, if we are having very low probability, let's say, because this graph, right? If you see this graph tends to 0, right? Here, this graph tends to 1, right? So if you are getting very high probability, let's say close to 1, which means this classifier is very confident, and with high confidence, this classifier is saying that it is the positive class. Similarly, if probability score is very, very low, very, very low means nearly 0, then this classifier again is very, very much confident, and with high confidence, this classifier is telling us that the input belongs to the negative class, right? So we want high probabilities for positive class and low probability for the negative class, right? Yes. So these two equations satisfy these conditions, right? Yes. So if actual class is positive, model is also positive, then we are having zero loss. Why are we having here zero loss? Because of this function minus log p hat, right? It is the form of this function, right? Minus log p hat, right? Because here in input, what we are using in input, we are using values from 0 to 1, right? So since we are using values from 0 to 1, so log function will be negative, right? So we want that value to be positive, so that's why here we are putting here negative sign, because negative, negative, positive, and finally you will get this function, right? Yes. And let's say if the actual output is positive but model is saying negative, in that case we are having here infinite loss, right? Because if you extend this function for exactly zero value, we will have infinite value here, right? Similarly, this is the function of minus log 1 minus p cap. So here, if model is saying negative, and the actual output is also negative class, in that case, we are here getting zero loss, right? So zero loss for let's say if the input belongs to the negative class and model is also saying the same, right? Negative class. But let's say if there is a mismatch, which means if actual output is the negative class, but the model is saying the positive class, again here we are getting infinite loss, right? So these two functions are satisfying our conditions. So that's why we are using these two functions in constructing our cost function, right? Okay. So this is our final cost functions where we have taken both function minus log p cap and minus 1 minus p cap, right? So here, if there is agreement between the actual label and the model predicted label, loss will be 0, right? So now there can be two cases where we will have agreement. So for example, actual is positive, model is also saying positive. Actual is negative, model is also saying negative. So in both of these cases, if you put here, let's say y is, so here y means actual label, p cap means model predicted label, right? So if you put here y1 p cap 1 or y0 p cap, if there is a mismatch, which means either actual label is 1, model is saying negative, or model is saying 0, or actual label is 0 and model is saying 1, right? So in both of these cases, we will get here a very high positive number. And what we want to minimize that mismatch, right? So for that reason, we will use this cost function. And using this cost function, we can use any optimization. So let's say we can use SGT algorithm, we can use batch gradient descent, we can use gradient descent to get the optimal value of theta. And what exactly we want? We want to minimize this cost function, right? Yes. Now, in today's session, we will see decision boundary, right? Okay, I'm getting one call, so just give me 1 minute. Yes. Yes. So now we will see decision boundaries. So decision boundaries are nothing but the boundaries where we are deciding something, right? So every classifier has its own decision boundary, right? So uh, and yes, we can learn we can learn machine learning model to solve problems. So for example, regression problem, classification problem, right? So we are solving these problems using ML model or using a classifier, and each and every classifier has its own decision boundary, right? So yes, let me give you one simple example. So let's say this is one classifier, and we are using this classifier to classify two classes, right? Let's say this triangle here are showing one class, and these rectangle are showing another class. So we are having here two classes, a green class and the blue class, right? And this dotted line here is the decision boundary, right? So using this boundary, we are deciding classes, right? So if input samples, green samples, as you can see here, if input lying above this boundary, which means green class. If input examples are lying below this boundary, this dotted line boundary, then the blue class, right? So here in 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 uh, in in solving these problems, what exactly we are learning? We are learning this boundary, right? Decision boundary. So each and every classifier has its own decision boundary, right? Okay. Yes. So here we will take logistic regression classifier, right? But as I said, we will have decision boundary for each and every classifier, right? But in this example, we will see logistic regression classifier, right? And the data set here we will use iris flower data set. So in this iris flower data set, there are 150 flowers and there are three classes, right? Satosa, versicolor, and virginica. So these are the three classes, and the total number of samples in this data set are the 150 samples, right? So we are having 150 samples, 50 samples for each classes. So there are 50 samples for Satosa class, 50 sample for versicolor class, and 50 samples for the virginica class, right? And the features here are the sepal length and petal length, sepal width, and the petal width, right? So these are the four features, right? So for each flower, we are having four features, and there are total 150 such flowers, and we are having here three classes in this data set, right? So we are solving a multi-class classification problem, right? Okay. Yes, so flowers we can categorize here in this data set three classes, as I said, versicolor, setosa, and the virginica. And we are using here four features: sepal length, sepal width, and the petal length, petal width, right? Yes. So this feature we are taking here, right? So in this data set, we are having petal length, petal width, sepal length, sepal width, right? Yes. So data set if you visualize this data set, we are having total 150 flowers. As you can see, there are total 150 rows, right? And in each example, in each flower or in each input, we are having four features: sepal length, sepal width, petal length, petal width, and this is the output class, right? So this output depends on these feature values. If you change these feature values, its class will change, right? Yes. So this is the output class, and these are the input features. So input, we are using four features, right? Yes. So if you visualize this data set, so yes, so you can load this data set from scikit-learn. So from scikit-learn, import data set, and from data sets, you can load this iris data set, right? Now, if you want to print the key associated with this data set, because this data set we are storing in the form of dictionary, right? So each dictionary has its keys. So if you want to print these keys, so there are data, target name, description, and feature names, right? So in data, we are having data values, right? So this sepal length, sepal width, petal width are nothing but the data, right? Input data points, right? So in data, how many rows we will have? 150 rows and 4 columns, right? So this is the data part. This is the target part, right? Yes. So in target, we will have output labels, right? So here we are having 3 classes, right? So here we are having 3 classes, Satosa, Virginica, and the versicolor. So we will assign here 0, 1, 2 numbering here, right? So for first class, we will use number 0. For the second class, we will use number 1. And for the third class, we will use label 2, right? So 0, 1, 2 labels we will use here. And yes, so if you print target, in target, we will get values 0, 1, 2. 0 means first class, 1 means the second class, and 2 means the third class. And target names, if you print target names, in target names, you will get these names, Satosa, Versicolor, and Virginica, right? Description, if you print description, it will describe this data set, right? Yes. And feature names are nothing but these names, right? Sepal length, sepal width, petal width, right? Yes. So using this command, you can print description and you will get the complete description of data set. And as I said, if you print data, you will get this tabular form, right? 150 rows and 4 columns, where each columns represent where each tuple or each row represent the data point. So first row is for the first data point, second row is for the second data point, and column is here the feature, right? So there are 4 features: sepal length, sepal width, petal length, petal width. So there will be 4 columns, right? Yes. If you print the feature names here, it will print sepal length, sepal width, petal width, because here we are using 4 features, right? Yes. If you print this target, it will print 0, 1, 2 values, right? So 0 for 0 target name, 0 means the first class, 1 means the second class, 2 means the third class, right? If you want to print these names, you will use target name. So since there are 3 classes, so 0 for Satosa class, 1 for Versicolor, and 2 for Virginica class, right? Okay, so any doubt? Okay. So now we will build a classifier to detect Virginica class based on only one feature, petal width, right? But in this original data set, we are having 4 features and 3 classes are there, right? 4 features and 3 classes are there. But for the sake of simplicity, here we are detecting Virginica class on the basis of petal width feature, right? So one feature we are using petal width, and we are predicting whether the input where the given flower is Virginica or not, right? So we are solving here a binary classification problem, right? We want to classify whether the given flower is a Virginica or not. So binary classification we are solving, and for that we are only using one feature, petal width. But yes, you can use 4 features, because there are 4 features we are having here, right? But for the sake of simplicity, we are only using here one feature, petal width, right? Okay. So for that, first we have to construct input and output data, right? Because the data set are given in standard form, right? So in data set we are having in fact 4 features and 3 classes are there. So we will convert the data set accordingly, right? Because here we only want one feature, so we will extract one that corresponding column. Because there are 4 columns, and since we are only using one feature, so we will extract one column, right? Okay. Yes. So here we are only using yes, only using petal width, and for petal width yes, for petal width, as you can see, we are having this third column, right? First column, second column, third column, and the fourth column. Petal width is the 4th column, right? So 0, 1, 2, 3. So third column we will fetch here, right? So 0 for first column, 1 for the second column, 2 for the third column, and third for the 4th column, right? Yes. So here we want all rows and third column, right? So using this this line, we can fetch the corresponding petal width column, right? So now our input is ready. We want now we will convert output labels, right? Because here output we are given in the form of 0, 1, 2, right? Because in output we are having three classes 0, 1, 2. So we will convert this output into a binary classifier output, right? Because in binary class output there can be only two classes. And here what exactly we are predicting here? We are predicting virgin ka versus not virgin ka, right? So for the virgin ka class we are having here first label, right? Label 1 is for the virgin ka class. So if label belongs to virgin ka class, which means true condition positive class. If label, let's say, is either setosa or sorry, for the virgin ka class we are using label 2, right? Because here what we want virgin ka type class, right? So for virgin ka label is 2. So if label is 2, which means positive class, and if label is either setosa or versicolor, then it is a negative class example, right? So if label is 2, which means positive class, or if label is either 0 or 1, then the negative class, right? Yes. So that's why here we are using if target label is 2, 2 means virgin ka class, then it is the positive class, else it is the negative class, right? So using this line, we can construct corresponding output label, right? Now, since here we are using logistic regression, so we will import logistic regression classifier from scikit-learn.linear model, and then we will fit this data point x and y, right? So any doubt in this code?
So random state is equal to 42 means?
Yeah, this we are using to ensure reproducibility, right? Because here yes, and in fact you can here let's say you can mention here any number, right? So let's say if you want to get the let's say same output for that region, here we will fix this seed value. So random state you can think like a seed value, because in your model or in your program, if you are having some random function, so random function always generate random number on the basis of seed, right? So if you change that seed, the distribution of that random function will change, right? So then you will get different values of random different random values, right? But let's say if you want to make sure that every time you will get the similar type of random values, then you will use a seed number, right? Because while calculating a random number, that random function will use seed value, right? So for that reason here we always use here random state, right? So random state is to ensure that each and every time we will get similar output, right?
Okay, sir. Yeah.
Okay. Yes. So now let's look at the model estimated probabilities, right? So here in because we are only using here one feature petal width, right? So in code also we have only used one column, one petal width column, and we are using binary outputs, right? Virgin ka versus not virgin ka, right? Yes. So if you print these probabilities, these outputs, if you print, you will get this type of curve. So as you can see here, in inputs we are only having one feature petal width, and petal width can be from 0 to 3, right? So because we have defined like that 0 to 3, right? And y side we are taking here probabilities. Yes, sorry. Yes, so y side we are having probabilities. Yes, and we are printing probabilities for both classes, right? version ka classes and not version ka classes, right? Okay. So we are plotting for both version ka classes and not version ka classes, right? Because in output, if you use this logistic regression classifier, you will get two probabilities, right? One probability is for the first class and the second probability for the negative class, right? So you will get both probabilities, one probability for the positive class, another probability for the negative class, right? But yes, if you sum these two probability, you will always get the one, right? So for example, let's say if 0.7 is the probability for the positive class, then 0.3 will be the probability for the negative class, negative and the other for the negative class, right? Yeah. Yes. So let's say for any input sample, if 0.9 is the probability belonging to the positive class, then 0.1 is the probability of that sample belonging to the negative class, right? And here we will always take the higher probabilities, right? Yes. So let's say for any given input x, let's say this classifier, logistic regression classifier, will output two probabilities because there are two output, right? Positive class and the negative class. Label 0, label 1, let's say. So here, let's say if this classifier is saying 0.9 is the probability of this input belonging to the positive class, then 0.1 will be the probability of this input belonging to the negative class, which means classifier is saying there are 90% of the chance that this input belongs to the positive class, right? So we will always take the majority, right? So we will always, so since classifier is saying with high probability, so we will predict it class positive, right? Yes, but it will output both probabilities, right? Probability of being positive class, probability of being negative class, right? So since here in case of positive we are getting higher number, so that's why we will use a positive class for this input, right? We will predict positive class for this input, right?
So in this output also, like now it's a 0-1 condition, no? A single logistic one. But we can also have like we can try to have it the 0, 1, 2, 1, 2, and 3. Is it possible to have it 3 level
No,
of
no, no,
this?
no, no, no. In logistic regression, we can only have binary output, right?
Okay. So rest of them we have to convert everything rest to 0.
Yes, so then one extension is there. So either we can use that extension to convert this binary classifier into multi-class classification problem, right?
Okay.
So or what you can do, you can use multiple binary classifier to solve a multi-class classification problem. So here what you will do, you will use three classifier because there are total 3 classes. So for first class you will use one binary classifier. For second you will use second binary classifier. For third you will use third binary classifier, right? So for example, using this classifier, what exactly we are doing? We are predicting third class, right? We are predicting virgin ka versus not virgin ka class, right? So if you use this classifier, very easily you can identify whether input belongs to the virgin ka class or not, right? Now we are left with the two classes. Let's say there can be only two cases. Either input belongs to the virgin ka class or it does not belongs to the virgin ka class. If input belongs to the virgin ka class, then we know its class is virgin ka. If input does not belongs to the virgin ka class, then we will use other binary class, right? Because there are three classes, so we will here create three binary classifier, one for each class, right? So this is the first method. The other method is the uh, to use the extension of logistic regression that we can use to solve the multi-class classification problem, and that extension is called the softmax regression, right? So softmax regression we can use to solve a multi-class classification problem, right? Any other doubt?
No, sir, clear it is. Soft maths, multi-regression.
Yeah. And this is the reason why we have converted input and output in this form, right? Because in output we only want two classes, one or zero label, right? So that's why we are using this condition that because in output what we want, virgin ka versus not virgin ka class. So if label is 2, which means positive class, and if label is either 0 or 1, then negative class, right? Yes, so this is why here we are writing in output we are using only two classes, 1 or 0. 1 for the positive class, 0 for the negative class, right? So don't confuse this 0 and 1 label with this 0 and 1 numbers, right? So here 0 means Setosa class, 1 means virgin ka class, and 2 means, 1 means versicolor class and 2 means virgin ka class. But in our case, here 1 means positive class and 0 means negative class, where 1 means virgin ka class and 0 means either Setosa or versicolor, right? Because we have converted multi-class label into binary labels, right? Yes. So if you plot the outputs predicted by logistic regression classifier, you will get this type of graph, right? One for the virgin ka class and one for the not virgin ka class, right? And this is the feature, petal width feature that we are using to predict virgin ka versus not virgin ka class, right? Now here, as you can see in output, we are having probabilities, input we are having features, right? Okay. So here, if you see these examples, so here we are having two classes, virgin ka class and not virgin ka class, right? So this triangle means virgin ka class sample, and this square means the not virgin ka class, right? Okay, so if here we are using triangle to show that the samples belongs to the virgin ka class, and this square we are using to show that these input samples uh, not belongs to the virgin ka class, right? Now this input samples may belongs to either Satosa class or versicolor class, but we don't care, right? Because here we are only solving a binary classification problem, virgin ka versus not virgin ka class, right? Yes. Yes.
So for some reason, if probability of both is 0.5, then how do we decide?
No, we cannot decide because that case lies on the decision boundary. So decision boundary classifier is confused, right? So this is the case where we cannot decide, right?
So what do we do in such cases?
So either we can use some predefined rule to break that tie, right? Because in that case, what you will get the class, right? So then you can use, let's say, if you can say that whenever we are getting tie, either we will go with the random selection, or let's say class, or we will go with the second class. So that type of rule you can define, right? Because this model will not help you in that case, right? If you are on the decision boundary, you both are equally probable, right? So let's say in this case also, let's say if you take this example, if any point lies on this decision boundary, then we cannot predict its class, because here we are defining this way. Let's say if point lies above this boundary, which means positive class. If point lies below this boundary, then the negative class. If point lies on this decision boundary, then model will not tell you anything, because both are equally probable, right? Both classes are equally probable on this decision boundary, right? Yes. We are having samples, positive samples and the negative samples, right? Yes. So the petal width of of virgin flower, here we are this virgin class we are represented by triangles. This ranges from, as you can see, from 1.4, roughly from 1.4 to 2.5 centimeter, right? So this is the feature value, Whittle width feature value from 1.54 to 2.5 for Virginica class flowers, right? Yes. So now, as you can see, this classifier is making wrong prediction for these three cases, right? For this flower, and for this flower, the classifier is making wrong prediction, right? Clearly, these three input belongs to the Virginica class, but classifier is classifying in other class, right? Not Virginica cases. But yes, if you consider these examples here, classifier is predicting with high probabilities, right? Because if you see this graph, for these data points we are having very high probability, right? I think probabilities is greater than 0.6 or 0.7 we are getting for these points, right? Yes. So, and yes, for this decision boundary, we cannot we cannot say anything, right? Okay, so here the rule is very simple, right? So here what rule we are using? We are using simple rule. If probability is greater than 0.5, which means positive class. If probability is less than 0.5, negative class, right? And yes, yes. So here, as you can see in this equation, we are having here equality condition, which means if we are getting 0.5 probability, equal probabilities, then we are always going with the positive class, right? But yes, you can also put this equal sign here, right? If let's say you are getting probability 0.5, you can always go with the 0, or you can do the selection randomly, right? So it depends on how you are designing this classifier. So let's say if you are designing this classifier in this way, then in case of tie, we will always go with the positive class, right? Yeah. Yes. So as you can see, for all these points, what classifier will predict? Positive class, right? Because for all these points, right hand side of this boundary, probability score is greater than 0.5, right? Because here we are having two probabilities. One probability for input belonging to positive class and one probability for input belonging to the negative class, right? So one probability we are getting for input belonging to the Virginica class. The other probability we will get for input belonging to the not Virginica class, right? And if you sum these two probability, you will get the one, right? So let's say if this number is 0.6, this number will be 0.4, right? 0.6 plus 0.4, 1 you will always get, right? Okay. Yes. So let's say if you take this input here, for this input, if you check here, you will get the value greater than 0.5, right? Which means if you use this classifier, it will predict for this particular input positive class, Virginica class, right? Yes. So for all these, yes. So as you can see, for all these data points, we will have here positive for Virginica class, because here probability threshold is greater than 0.5, right? So if you see this example, here if you calculate this probability value, this probability values is greater than 0.5, right? So let's say if this value is 0.55, this value will be 0.45, right? Let's say this value is 0.55, this value will be 0.45, because if you sum these two, you will get the 1, right? But since this way score is greater than 0.5, which means positive class or virgin ka class, right? Similarly, if you see this this input point here, also we are getting probability score greater than 0.5, right? So for all these points, model is predicting correctly, right? Now this input is lying over this decision boundary. So here, if you calculate this score, you will get the 0.5 value. You will get 0.5 value, right? So since this point lies on the decision boundary, so actually the classifier is confused. But since we are breaking tie in favor of positive class, right? Because in equation we have written equality condition for the positive class, right? So if probability score is 0.5, then we will predict positive class, right? So we are defining like that. So that's why for this point also model will predict positive class. So what we can say that for all these points, model will predict positive class. And for these 2 points, model is predicting wrong. Model prediction is wrong. These 2 points belongs to the virgin ka class, but model will, but using this model, the prediction will be the not virgin ka class, right? Because if you calculate probability here, probability of being virgin ka class is less than 0.5, or in other word, probability of being negative class is higher than the positive class, which means model will predict that this input belongs to the not virgin ka class. Similarly, model will predict this input belongs to the not virgin ka class, right? Because here we will get higher probability for the negative class, right? So this probability is less than 0.5, which means negative class. Here also this probability is less than 0.5, which means the negative class, right? Any doubt in this example? Right. So for this example, model prediction is correct. This model prediction is correct. So for all these examples, model prediction is correct. Only if you consider these 2 examples here, the model will predict, model prediction will be wrong, right? Similarly, here if you see samples, input samples belonging to the non-virgin ka class, for all these data points, model prediction is correct, right? Model is predicting correctly, right? Because if you use this logistic regression, and if you calculate the probability here, you will get the probability less than 0.5, right? So less than 0.5, which means negative class, less than 0.5 negative class, less than 0.5 negative class, which means for all these points, model prediction is correct, right? Model will correctly predict negative class, right? Now, can you tell me what will be the model prediction for this input sample? Actually, this input belongs to the not virgin ka class. But if you calculate probability here, what probability we will get? Greater than 0.5, right? Greater than 0.5 probability we will get here, which means model will predict this input belongs to the virgin ka class, right? So model will make here mistake, right? So model will make a mistake here, model will make mistake here, and this input again belongs to the decision boundary. So ideally, we cannot predict its class because classifier is confused. But since we have defined like whenever we are getting tie, or whenever we are getting 0.5 score, we will always say positive class. For this input, we will get 0.5 probability. So we will say its class is the positive class. So again, in this case, model prediction will be wrong because this class belongs to the negative class, but model is saying positive class, right? Okay.
So the dark green line represent exactly what?
Yeah, so dark green line represent the probabilities values for the virgin ka class. right? And this dotted blue line represent probability value for the not version ka class.
Okay.
Right. So we don't have to consider both probabilities. We can even use the one probability, right? So here you can only use dark green line for making prediction, right? So here, let's say if you only use a dark green line, then prediction rule is very simple. If probability, because this dark green line is for the virgin ka class, right? This dark green line we are using for the virgin ka class, which means if probability is greater than 0.5, which means virgin ka class. If probability is less than 0.5, which means not virgin ka class, right? If you use this dark line. If you use this dotted blue line, then the rule will change, because this dotted blue line is for the not virgin ka class. So if you are using this dotted blue line, then if probability is greater than 0.5 for the dotted blue line, which means not virgin ka class. If probability is less than 0.5 for dotted blue line, which means virgin ka class, right? So rule will change if you use dotted blue line, right? So in fact, while defining logistic regression classifier, we only considered probability for the positive class, right? So logistic regression classifier, we only use this solid green line, right? We only used probability for the positive class classifier, right? Because this green line we are using for the positive class, right? So if you consider this blue, this green line, if you consider here, what rule you will check here? If probability is greater than or equal to 0.5, which means the virgin ka class, and if probability is less than 0.5, which means not virgin ka class, right? But you can also use this dotted blue line, but then rule will change, right? Because the dotted blue line is for the not virgin ka class, which means if you use this dotted blue line, and if you are getting probability greater than 0.5, which means not virgin ka class, less than 0.5, which means the virgin ka class. Or you can use both lines, right? If you use both solid green line and dotted blue line, here you will compare the probabilities, right? So let's say if probability is higher, which means virgin ka class, probability is higher for the dotted line, which means not virgin ka class, right? Because here you are getting two probabilities, right? One probability for virgin ka class, the other probability for the not virgin ka class. So let's say if you pick any sample, so let's say if you are taking this sample, here the probability of virgin ka class is higher than probability of not virgin ka class, which means class label is virgin, right? Or let's say if you pick this example, here the probability of virgin ka class is lesser than probability of not virgin ka class, which means we are getting a higher probability for the not virgin ka, right? Which means class label is not virgin ka, right? Because these are the two probabilities. If you sum this probability, you will get the one, right? One probability for the positive class. So this is the probability for the negative class. If positive class probability is higher than negative class probability, which means input belongs to the positive class. And if negative class probability is higher than the positive class, then which means input belongs to the negative class, right?
Dr. Pravendra,
Yes, yes.
yeah, sorry to interrupt. We have received the quiz link, so do we have to take it right away or at the end of the class?
Okay, so what is the quiz duration?
I don't know. I think it doesn't mention that.
Okay, so today you have quiz, right?
Yes. So I just received the link on the mail.
Yes. Okay, so let's take a 5-minute break, and I will ask Gajendra, right, regarding that.
Okay. Thank you, sir.